This video is a continuation of the previous video looking at linear regression. If you want to work alongside with us, please go to drstephpowers.github.io/BIA. We are working here in chapter 10 under regression. So click on that. You can open it up in Google Colab and then make sure that you log into your Google Drive and save a copy so that you can run and edit the code as you want. You will need a data set. That data set is found here on the left under data, and you can see right here it says fundamentals. When you go to that particular location, you can download the data set and you can dump it into your Google Drive. In our previous video, we linked our Python workbook to our Google Drive, so we've already imported it in. In this particular video, we're going to look at the assumptions that come with linear regression. So when we create a linear regression model, we are assuming that our residuals, that our measurement error has constant variance. Okay, this is called homoscedasticity. That the data is normally distributed. If the underlying data has a normal distribution, then the residuals or measurement error will also have a normal distribution. And that's what allows us to use linear algebra, because that linear relationship is based on normality. And then we're assuming that the variables we're using to predict whatever we're predicting are independent of each other. That is, we do not have multicollinearity. The independent variables are truly independent of one another. So we need to look at our residuals and see if our assumptions are correct. So what we do is we're going to plot our residuals and we look at the residuals. If there is a pattern to the residuals, then we have the wrong model. So this particular one here would show us the linear model is not appropriate. The underlying data is not normal. It has some kind of other pattern to it. We can also assess the normality of the distribution by creating what is called a QQ plot. So a QQ plot looks like what you see below my face here. And what it does is it looks at here's how the data is distributed versus here's a normal distribution. In fact, it's a T distribution rather than a normal distribution. If they matched, then the data points would fall here along this 45-degree line. If they don't match, then what we have is a curve, and that tells us that we have violated the assumption of normality. The other thing we are checking as we look at our data is we are looking for homoscedasticity. If when you look at your residuals, your measurement error, that it is not random scatter, but instead we have on one end, there's little variability, and on the other, lots of variability, then we don't have constant variance. We don't have constant variability. This is heteroscedasticity. That is the variance is changing. Okay? So let's take a look at our data set from the model we were working on and see how we are doing in terms of those assumptions. So let's go to our data. So when we left off in the last video, we had created a algorithm here to predict earnings per share as a function of return on equity and year and the interaction between them. So we had this model that we know does not fit well because our R squared is only 0.01. We do have three variables that are statistically significant: return on equity, the year, and the interaction between them. But it's not explaining much of the model, even though it is significant. Now, as we pointed out in the previous video, we are not really using this data correctly because, one, all the variables in this data set are highly correlated, so we have multicollinearity. Remember, one of the assumptions is that the variables are independent of each other. And then the other thing we have is that in this particular data set, we have that basically we have kind of 5 rows that are the same company, just different times in the year. And our model does not currently acknowledge that a bunch of the data is one company and a bunch of the data is another company. So what we have is that variable, right, that is like the company, that explains most of the variability, right? So Apple and Nova chemicals they're going to have different earnings per share. Those 5 years or so are going to be similar for Apple, similar for Nova, but not like each other because they're completely separate companies, separate industries. And so those variables we don't have in our model. And so we know the model is not going to fit well, right? Just because we're using the data incorrectly. All right, we're assuming every row is a completely different company. So let's go and look at the model we created in our last video. So we created this model here, this one here. And so we want to look at our assumptions for this model. Well, we can take our residuals from this model. So the model, we called it OLS reg. We used SMF. We called the model, we fit the model, we got a summary. So that's where we left off in our last video. So now let's take that OLS underscore reg and have it give us the residuals. Okay, we're going to call them res. And then we're going to do a plot using SM. So if I go back in the code to right here, this is where I imported it. So make sure that you import statsmodel.api as SM, and you're going to need, I'm just going to pull the whole thing, and you're going to need skippy.stats as stats. That's going to give you your t distribution. So to create my QQ plot, I need matplotlib.pyplot as plt. I need statsmodel.api as sm. I need skippy.stats as stats. Okay. Then I'm going to pull the residuals from the model. I am going to use SM to create a QQ plot. And that QQ plot is going to plot my residuals versus what a t distribution should have. And we want it to be a 45-degree line added to this so that we can see where they should be. Okay, so if we look at this here, what we should see is that all these blue dots should random scatter close to this red line. Notice that this part here is all below the line and this part up here is above the line. So likely we don't have normality here. We're starting to see kind of the shape, and so we have an issue with that assumption. Sometimes you can, if it's close enough, you know, if it's a little bit above, a little bit below, kind of wave around good enough. We do look at the fact here that this is all below and that's all above. That kind of tells you that, that you're not really truly normal. If we were to plot the residuals, we're looking for random scatter along the 0. Some of our estimates should be above, some of our estimates should be below. So we're going to use that matplotlib.pyplot to plot our residuals and add a horizontal line at 0, and we're making that a black line. So here you can see it here. We have some extreme residuals that are far off. The other thing we're looking for is, do we have that homoscedasticity? So we should see just as much variability here on the left as we see on the right. If we lost this data point right here, then we would be pretty similar on left and right. It is kind of, there's these high ones here, and the middle doesn't seem to have that. So there is some kind of shape here that isn't necessarily being captured in our data. So when we're doing our linear regression, there we should be checking, if we just go back, check for homoscedasticity, so random scatter, not a shape. Check your QQ plot for normality. Check to make sure there's not a pattern in your residuals. That would say you need, instead of a linear one, maybe you need a polynomial or logarithmic or exponential shape to your model. Okay, so we want to check those assumptions in addition to checking how well the model fits. This model has lots of problems. The variables don't predict much of it. And as we look at that QQ plot, we have issues here with normality as well.